Good morning, everyone. Today we are going to start the examples which are based on the Laurent's theorem, not about the Laurent series, but about the Laurent's theorem. We have to use the result of this Laurent's theorem in our examples, right? So let's start. The example is, show that sine of c into z plus 1 over z, where c is any constant, can be expanded in a series of the type summation 0 to infinity on an z the power n plus summation which starts from n equal to 1 to infinity bn into z the power minus n, in which the coefficients of both z the power n and z the power minus n, that means the coefficients for z the power n is an and for z the power minus n is bn. Both these coefficients have the value 1 over 2 pi integration 0 to 2 pi on sine of 2c cos theta into cos of n theta d theta. This we have to prove. Now one remark is given to us. This remark is very helpful. Integration from 0 to a on fz dz is equal to 0 if f of a minus z is equal to minus of f of z. If I put instead of z as a minus z, then I will get my result to be minus of fz, right? For example, I am having the integration on sine z from 0 to 2 pi dz is equal to 0. Now this integration is 0 as sine of, put a minus z instead of z. What is your a match? A is 2 pi. So I am putting sine of a minus z as 2 pi minus z, which is equal to minus of sine z. That means negative of our original function, which was sine z, right? So whenever such kind of thing is happen, we have to put that integration is equal to 0, right? Okay. So let's start with the solution. In this diagram, I'm having annulus, having the radiuses small r and capital R, where small r is less than this capital R. And this is your first circle, that is C1. And this is centered at, this annulus is centered at 0. And we are having any point z in this annulus, right? So since what is the function given to us? Sine c into z plus 1 over z. This is analytic everywhere except, yes, where the function is not defined, except at z equal to 0 and z equal to infinity. At both these points the function is not defined. That's why I have written this function is analytic everywhere except z equal to 0 and z equal to infinity, because at these points function is not defined. So since therefore sine of c into z plus 1 over z, this is analytic in the annulus. So it is analytic everywhere. So I am writing this is analytic in the annulus, which I have drawn. So let's, r is less than equal to mod z less than r, where this is positive, which is greater than 0, and this capital R is less than infinity, right? Where we have to write r is small and capital R is large. So if the function is analytic in this analysis, can I write, if I remove the 0 and infinity, I can also write this as thus fz can be expanded in a Laurent series in the analysis small r less than mod z less than capital R. Right? Now we have to use our Laurent's theorem, which says that, hence by Laurent's theorem, the function is equal to summation n starting from minus infinity to infinity a n z the power n. This is the Laurent's theorem, right? And the function is given to us as sine of c into z plus 1 over z, right? This is further equal to, alright, my summation is from n equal to minus infinity to infinity. If I open that summation, and also if I open these two summations and get their sum, the result will be the same. See, here the summation is starting from 0 to infinity a n z the power n plus summation starting from 1 to infinity a minus n z the power minus n. If you put the values of n, you will get the same result in these two, sum of the summation and also the previous one where n is starting from minus infinity to infinity a n z the power n. If you open this, you will get the same result as if you open these two summation, right? So you just have to change this n to minus n here and start the summation from 1 to infinity, right? So all the values are covered. So this is equal to summation n going from 0 to infinity a n z the power n plus summation n going from 1 to infinity. I take a with minus n as b and the coefficient z the power minus n. The coefficient for z the power minus n is a minus n. So I take this as bn. Alright. So where according to the Laurent's theorem, your coefficient an is equal to 1 over 2 pi iota integration on c1 sine, that is your function, c into z plus 1 over z dz over z the power n plus 1. According to Laurent's theorem, this coefficient is equal to this. And second coefficient bn, this is equal to a minus n. So for the first coefficient an, I take the c1 circle, right, the inner circle, and I take, suppose that c1 circle to be centered at 0 with radius 1. So here z is equal to 1. I take the radius 1. So as mod z is equal to 1, because my radius is greater than 0, small r is greater than 0, I took small r equal to 1. So this is z is equal to, in polar form, z is r e the power iota theta. Because r is equal to 1 I have taken, so this is z is equal to, put r equal to 1 into e the power iota theta, which is e the power iota theta. So z is e the power iota theta. So we have to put this z in this coefficient because I need my coefficient an, which I have to prove according to the question. So I am putting the values now. An is equal to 1 over 2 pi iota integration from 0 to 2 pi sine c z. What is z? E the power iota theta plus 1 over z will be z inverse, which is e the power minus iota theta. And then you are having dz, right? See, dz over z the power n plus 1. If you derivate this z, you will get iota e the power iota theta over z the power n plus 1. So e the power, sorry, z the power n plus 1, that is e the power iota n plus 1 theta, right? This is equal to 1 over 2 pi, iota iota cancel, right? 0 to 2 pi sine of, this is 2c cos of theta e the power minus n iota theta. D theta. In the denominator I am having e the power iota n theta and e the power iota theta, that is cancelled, and e the power iota n theta will go to the numerator and sign gets changed, and this is e the power iota theta plus e the power minus iota theta over 2. I know that this is equal to cos of theta, so I write instead of this as 2 cos of theta into c. This is your formula, which is equal to 1 over 2 pi integration 0 to 2 pi sine of 2c cos theta. Now the next step is, I know that e the power minus n iota theta will be Euler's from your Euler's formula. This is cos n theta minus iota sine of n theta d theta, right? Further, 1 over 2 pi integration 0 to 2 pi sine of 2c cos theta, cos of n theta, separate them, minus iota over 2 pi, this iota I taken outside, sine of 2c cos theta sine of n theta d theta. Now I need only this first integral, second should be 0, right? Now how this second integral should be 0? We have read our remark that if we put f of integration from 0 to a, f of a minus z, if this integration is equal to f of minus f of z, then that integration is equal to 0. So let's check as, put instead of theta as a minus theta, that is 2 pi minus theta. So this is, let's check, sine of 2c, instead of cos theta I check cos of a minus theta, a is 2 pi here, so 2 pi minus theta, and sine of n 2 pi minus theta. This is equal to minus sine of 2c cos of theta sine of n theta, because sine of 2 pi is 0 and cos of 2 pi minus theta is minus of sine theta. Sorry, cos of 2 pi minus theta is minus cos of theta, right? The fourth quadrant. So this is nothing but your minus of this whole function. Yes? So this thing is equal to 0 then. And so what is your an comes out to be? An is equal to 1 over 2 pi integration 0 to 2 pi sine of 2c cos of theta cos of n theta d theta minus iota over 2 pi. That whole integration is 0 because we have used the remark, that is integration from 0 to a, f of z dz is equal to 0 if f of a minus z comes out to be equal to minus of fz. Right? So finally I got an as 1 over 2 pi, which is my required result, sine of 2c cos theta cos of n theta d theta. So first coefficient done. Now the second one, bn. This is equal to a minus n, right? So I just have to put instead of n as minus n in this an. So this is 1 over 2 pi integration 0 to 2 pi sine of 2c cos theta cos of minus n theta d theta, and we know that cos of minus theta is cos theta. So this is equal to 1 over 2 pi integration 0 to 2 pi sine of 2c cos theta, and this will be cos of n theta d theta. Right? Hence we got both the values for the coefficients an and bn to be the same. Right? So finally, hence our function sine of c z plus 1 over z, this is equal to summation n going from 0 to infinity. I can write a n z the power n here plus summation n going from 1 to infinity. I can write b n z the power n minus n, right? Where an is equal to bn is equal to 1 over 2 pi integration 0 to 2 pi sine of 2c cos theta cos of n theta d theta. So are both the coefficients having the same value, which is the required one. Hence the result. Alright, thank you.